Okay, so welcome to lecture 11.5. This is a completely optional lecture. You don't have to watch this. You will not be tested or quizzed over any of the information in this lecture, but if you are curious as to why the derivative of e to the x is itself, then keep watching. So the story that of this number e is kind of an interesting one. So maybe before we get to why this derivative is true, I should give a little bit of a backstory. So backstory, and the story is of compounding interest. So this was a question asked by one of the Bernoullis. There were like four of them that were mathematicians. They were all brothers, and one of them was a father. I forget how the family tree goes, but one of the Bernoullis, all of them somehow made important contributions to mathematics. Asked the following, or really he didn't ask, he presented the following scenario. The following scenario. So suppose, firstly, suppose $1, I forget what nationality Bernoulli would have been, but his currency most certainly was not the dollar, but for our purposes, we'll just use the dollar. So suppose $1 is invested at a 100% interest rate. So that is, every time the interest is compounded, you're going to get 100% of whatever you invested. I wish we had that today. Such things do not exist in the real world, but anyway, so suppose $1 is invested at 100% interest and compounded once. So that is, I'm going to take the amount of money in there, I'm going to multiply it by 100%, and I'm going to add that to your total. So the total investment, or total, I don't know, value, we'll just call it T, becomes, well, T is equal to 1, and then I add 1. I just compound the 1 by 100% and then add it once. So this is equal to 2. So if I invest $1 at 100% interest and then compound it once, I will get $2. Simple enough. Well, suppose $1 is invested at a 50%, should be interest rate, and compounded not once, but twice. So that is, I'm going to take your initial investment, I'm going to multiply it by 50% and add that. That's the first compounding. And then that new total, I will take and multiply it by 50% and then add that to your total. So our total, so then T is, well, how do we compute T? T is given by, well, I start at 1, and then I add 50% of 1, and then that's the first compounding, and then I take this new total, I multiply that by a half, and add it back to my new total. So add back the 1 plus a half. So this is the investment after the first compounding, and then this is the amount of interest earned after in the second compounding. So amount after first compounding interest earned at second compounding. I'm not going to write that word again. And so, well, notice what do we have here? We have 1 plus a half, and then if I think about sort of a way I could factor this, I have a 1 times 1 plus a half times 1 plus a half. And so really, this is actually 1 plus 1/2 squared. And if this is not obvious to you, you can actually just sit down and compute this, and you'll find that you do indeed have this identity. And maybe we should put subscripts on these, so T1, T2. Now, the next question that you should ask is, well, suppose that we do this again, and we instead now invest at, well, we can't do exact fraction of 100%, but 100% divided by 3. So suppose $1 is invested at 33.333 ... percent, and compounded 3 times. We won't do this again after this. I just wanted to really illustrate the point. 3 times. Then T3 is, well, how do I compute that? It's going to be a little bit longer of a calculation, but we can do it. So I take my initial value, 1. I add 1/3 of it. And then so this is the first compounding. And then I'm going to add 1/3 of this amount. This is the second compounding. And then the third time I'm going to take and add 1/3 of this whole amount. So 1/3 of 1 plus 1/3 plus 1/3 of 1 plus 1/3. So all I've done is just copy this bit into the parentheses here. And indeed, if you were to go and work this out, you would find that you would get 1 plus 1/3 to the power of 3. And you can ask, what happens if I just let this denominator right here, this 3, tend off towards infinity? So what happens as 1, 2, 3, ... goes to infinity? That is, the number of times I compound and the interest I gain, or the percentage interest rate every time is 1 over the number of times I compound. What happens as this goes to infinity? Well, that is, we can express this as a limit. Let's go ahead and do that. So that is what does the limit as n tends to infinity of 1 plus 1 over n to the power of n look like? If it looks like anything at all. This limit need not actually exist. But it turns out that this limit is finite. It's a number. It turns out that this limit is finite and equals a real number. This number, which this limit converges to, we define this number to be the number e. E is defined to be, so an equal sign with a little colon on it. It is defined to be this limit, whatever this limit happens to equal. And there's another way in which we can write this. So as n goes to infinity, notice that 1 over n goes to 0. So I could also sort of flip n and 1 over n and change this from n going into infinity to maybe x going to 0. This is going to be 1 plus x to the power of 1 over x. So these are the exact same limit, but just two different ways of writing it. And the number e, which is, you know, approximately 2.78 ... I think, it's, you know, it's some number. Now, why is this important, and why does this mean that the derivative of e to the x is its own derivative? Well, suppose that we wanted to actually find a function that was its own derivative. So suppose we wanted to find a function that was its own derivative. And it's not quite obvious where we would start looking, but one thing that you might consider is exponential functions. So let's try to find one of the form a to the x for some number a. So let's just suppose that our function has this form. It makes certain computations nice, so it seems reasonable enough that this would be a good guess. So what would we actually want if the derivative, if a function was its own derivative? So then we want, well, what do we want? We want a to the x equal to the limit as h goes to 0. So we just put in the definition of the derivative. So this is a to the x plus h. This is my f of x plus h minus a to the x over h. And notice what happens here. If I have an exponent and I'm adding two things together, then this breaks apart as a product, and I can factor the a to the x out. So let's write out all the steps here. So this is a to the x times a to the h minus a to the x over h. And the a to the x, well, that's not changing with respect to h. So this actually just comes all the way outside of the limit. So we want the limit as h goes to 0 of a to the power of h minus 1 over h. Well, divide by a to the x on each side. So we need the limit as h goes to 0 of a to the h minus 1 over h equal to, well, if I divide by a to the x, I get 1 on the left, equal to 1. Okay, so what does that mean? So this means that for small h, that is h very close to 0, we want a to the h minus 1 divided by h to be approximately equal to 1. Okay, well, if I just sort of finagle this around and try and solve for a, what happens? So that is, we need, well, let's multiply by h on each side. So a to the h minus 1 is approximately h, that's all I've done here. Let's add 1 over. So a to the h is approximately 1 plus h. And then let's take the hth root of a to the h. So just like you take a square root to cancel out a square, let's take an hth root to cancel out the h here. So a should be approximately 1 plus h to the power of 1 over h. Aha! This is exactly what we have up here. For small h, this is precisely what this limit is saying, is that as I take h smaller and smaller, x or h, it doesn't matter which symbol I use there, it's completely arbitrary. As I take smaller and smaller h values, I approach this value. So, thus, we see that we should take a equals e. Now, this is by no means a rigorous proof. It can be shown that the two limits, the limit as h goes to 0 of e to the h minus 1 over h, that this limit equaling 1 is equivalent. So that is, each of these implies the other. This is equivalent to the limit as h goes to 0 of 1 plus h to the 1 over h equals e. So you can show this. I'm not going to do that. It's a somewhat more involved computation, but you can show that this is true. And so really the reason why why e is its own derivative is precisely this argument, is that as you take smaller and smaller h values to get this a, then the process you are actually doing is precisely the process that can be used to compute e. Okay, so that's why the derivative of e to the x is its own, or is itself. Hope you guys enjoyed this video. Again, completely optional, but hopefully it was educational and informative.